Good afternoon. My name is Guillaume Chanel. I am the supervisor of this work entitled Multimodal Emotion Recognition using Recurrence Plots and Transfer Learning on Physiological Signals. This work was done by Ryan Elalami and in collaboration with Marios Fanourakis. Unfortunately, they were not available to present it, so I will do it today. It's work done at the Computer Science Department of the University of Geneva, and it's also a collaboration with the company Logitech on a project which is named Emotionally Intelligent Peripherals for Video Game Streamers and Players. The goal of this project was to collect multimodal data from hundreds of players in competitive gaming, and then to train deep learning models based on this big data, deep learning models which would be able to recognize emotions of players. The final objective was then to create interfaces to better connect streamers and followers, spectators, by enhancing emotion awareness. Unfortunately, this project started in 2020, and as most research projects, we had to face difficulties to collect data, so that we came up with this coping plan, which is to evaluate transfer learning approach on physiological signals, but this time using existing databases. When you look at the state of the art of transfer learning, particularly transfer learning on physiological activity, you will notice that most studies convert physiological signals to images using spectrograms. So to take an example, they first, for instance, record ECG, which is a measure of cardiac activity, electrocardiography. And from this signal, they apply a short-term Fourier transform to obtain a spectrogram, which is then an image, and you can then feed this image to a usual network like VGG16 or ResNet, which have been trained of tons of images taken from the internet, for instance, which gives you some feature which you can use with a classical machine learning algorithm to classify emotions in your smaller dataset. So this has several advantages. For instance, it allows to represent signals of different lengths with a fixed image resolution. And as I already said, it's nice because you can use pre-trained network on huge image databases. But it also has disadvantages. For instance, you need to define some parameter to apply a short-term Fourier transform, like the window length or the type of window function that you want to use. And more importantly, it's not well suited for non-periodic and non-stationary signals. And it happens that one very important signal in emotion assessment from physiological signals is electrodermal activity. You see here an example of electrodermal activity. And this signal is highly non-stationary and non-periodic, so that when you use a short-term Fourier transform on it, the result might appear as not that good, or at least it doesn't represent all the signal correctly. An alternative to create images is to use recurrence plots. Recurrence plots, they come from the field of nonlinear dynamical systems. And in this field, a signal is generally considered as an observation of a complex system. And this complex system is represented by its state space. As such, the recurrence plots are generally computed from the state space itself. The problem here is that to obtain the state space, we need again to define several parameters. Fortunately, it's also possible to compute recurrence plots directly from the signal, and that is what we did here in this study. So how do you compute a recurrence plot? Well, it's in fact quite simple. To generate an image like the one on the right, which is a recurrence plot, for each pixel yj, you actually compute the distance between the values y and j in the signal. And you do that for any possible pair. And if this distance is higher than the threshold epsilon, then you put a 1 in the matrix, otherwise you put a 0. So as you can see, there's this binarization step that occurs here. In the literature, what people do from this image when they are studying physiological signals for emotion assessment is that they then extract features from this image using a technique called recurrence quantification analysis. And it means extracting, for instance, a recurrence rate, which is the percentage of white dots or yellow dots in this image. The percentage also of dots that forms diagonal, or percentage of dots that forms vertical shapes or horizontal shapes in the image. So basically they used engineered feature. And that's not what we want to do, because we want to use pre-trained network to perform transfer learning and extract some features. Also, a problem is that here, as you see, there's still this parameter that we need to use, the epsilon value. And in fact, it happened that this binarization step can be simply omitted by computing the distance between the points in these signals. And in that case, you will obtain this image here on the right, which still conserves a lot of the structure you've seen before and contains all the information of this signal. You can then use directly pre-trained network like you would do on spectrograms. To sum up, recurrence plots have advantages over spectrograms. They can be used without any parameters, and they are well suited for any type of signals, including periodic and non-periodic signals like electrodermal activity. However, the efficiency of recurrence plots was never compared to spectrograms per se. And also, transfer learning was not much investigated on recurrence plot for physiological signals analysis. Hence, our two research questions: is it possible to use recurrence plots for transfer learning? And are recurrence plots more efficient than spectrograms? And we have two hypotheses. The first one is that, yes, it should be possible. A pre-trained ResNet 50 model should be able to extract relevant features. And we expect that recurrence plots should be particularly efficient for electrodermal activity because it is a non-periodic signal. To test this hypothesis, we use data from two databases, the DEEP and the Amigos databases. Both datasets are constituted of physiological signals recorded while participants were stimulated with videos. Notice that in the case of the Amigos database, the videos had different lengths, but it's not a big deal because we could resample these to fixed width images. Both databases also had electrodermal activity and cardiac activity. Notice here that for the Amigos database, the cardiac activity was recorded using ECG. I already mentioned these signals before. But for DEEP, it was PPG, photoplethysmography, which is an alternate measure of cardiac activity. But we can, so I will just mention the umbrella term cardiac activity to refer to these two types of signals. In terms of targets, in terms of what we want to predict, both databases ask their participants to evaluate their emotions in the valence arousal space. You can see here an example. And don't get confused by the different colors, the four colors of this graph. We didn't use the classes classification task. We did, in fact, two tasks, one which consists of separating low versus high valence, so the blue dots versus the yellow and green dots, and high versus low arousal, so the lower part of the graph here versus the higher part of the graph. In terms of data processing, we first downsampled all signals to 120 Hz. We applied local filters to remove high frequency noise, matching a bit the shape of the signals. We also normalized all the signals between 0 and 1, and we then compute RGB images rescaled to 224 by 224 pixels. We obtained this data, images for electrodermal activity, images for cardiac activity. Some of these images were spectrograms, and also some of them were recurrence plots. And we can then feed all these into a ResNet50 model, which gave us more than 2,000 features for electrodermal activity and the same amount of features for cardiac activity. We then performed the PCA in this high dimensional space because we don't have that many points. So to avoid the cost of dimensionality, we performed the PCA. The PCA was done independently for the two types of signals so that we obtained 30 EDA features and 30 ECG features. And then these features, as I mentioned before, were fed to a classical machine learning algorithm, logistic regression, in this case, to predict either low or high arousal or valence. First, we wanted to compare our results, and particularly the results of recurrence plots, to the state of the art. So we compared to two studies, which we found were quite similar to what we did, but using spectrograms. One was using a 1D CNN on the original signals, and the other one was computing spectrograms and using that as images to pass then to a VGG algorithm for feature extraction. And these two also studies were applied on the Amigos dataset. So here the results are only for the Amigos dataset. What you can see is that the recurrence plots performed more or less in the state of the art. So in terms of valence, we are in between the two studies always. And in terms of arousal, we reached actually the best accuracy for electrodermal activity here, and a bit less for the cardiac activity, although it's not far from the state of the art. So our conclusion here is that yes, the ResNet50 model was able to extract relevant features from recurrence plot. And these features were actually able to reach state-of-the-art performance. Now, if we compare recurrence plots to spectrograms inside our study without looking at the state-of-the-art, and here the results are averaged over the two databases. So that's why there's little error bars here. Okay, these are due to the two performance values, one for each database. And what we observe is that either you use recurrence plots in blue or spectrograms in orange. Whatever you use, for cardiac activity, the performance will be the same. And here also, there's a small difference, but this difference is actually not significant, even for arousal. For electrodermal activity, the story is a bit different. For both valence and arousal, we have a significant difference, and the recurrence plots were performing better than the spectrograms, exactly as was expected from our hypothesis. So we concluded that the performance is improved by using recurrence plot for non-stationary signals like electrodermal activity. In conclusion, our first research question was, is it possible to use recurrence plots for transfer learning? The answer is yes. A pre-trained ResNet50 model was able to extract relevant features. Are recurrence plots more efficient than spectrograms? The answer is yes again. Recurrence plots should be particularly efficient for electrodermal activity. And thus, we advise you to use recurrence plots when you want to perform transfer learning on physiological activity, possibly replacing spectrograms or combining them with spectrograms, particularly when you are using non-stationary signals like electrodermal activity. Thank you very much for your attention, and I should now be available to answer any question.